So the ultimate question, right? How the physical, kind of gray, silent brain in your skull conjures up this entire vibrant universe you inhabit. It's arguably the greatest scientific and philosophical challenge we face.
It really is.
Welcome to Brain Binge. We're the show where we extract the core knowledge from your sources, and today we are focusing on the absolute cutting edge of consciousness research.
And our mission really is to move you beyond just simple definitions. We're going to be navigating the territory from, the basic biological mechanics through the leading and often competing theoretical frameworks.
And from there, we'll get into the revelations that we find in altered states, which is always fascinating.
Absolutely. All before tackling some of the most speculative ideas at the intersection of mind and quantum physics. We're giving you the shortcut to understanding the mind's architecture.
Okay, let's unpack that and jump right into the definitions, because science really needs boundaries to work with. And your sources make it very clear that neuroscientists typically break consciousness down into two crucial, very distinct components.
That's the perfect place to start. It's wakefulness versus awareness. And they sound similar, but they're fundamentally different things.
Okay, so wakefulness is what?
Wakefulness is purely about the operational status of the brain. It's, Are you physiologically online? Are you not in a coma, not under deep anesthesia, not in the deepest stages of sleep? It's essentially the mechanical ability of the entire system to even run.
It's the power being on. The computer is booted up, but no software is necessarily running yet.
That's a great analogy. And awareness, then, is the software. It's the experiential side. This is the subjective, the first-person experience. It's the feeling of seeing the color red, the sense of having a thought, that internal monologue that's running in your head right now.
That's the qualia. It's the what it's like to be you.
Exactly. And this separation is so critical because it reveals that consciousness is, it's a dynamic, braided process. It's not just an on or off switch.
Right, because you can have one without the other.
Precisely. We see patients who retain full wakefulness. They have sleep-wake cycles, their eyes might open, but they show absolutely no reliable sign of awareness.
A vegetative state.
The vegetative state. And conversely, think about when you're having a really vivid dream. You might have very low physical wakefulness, but your internal awareness could be extremely high, maybe even more intense than your waking life.
It's the interaction and the balance of these two systems that defines what we think of as our typical conscious state.
Yes. And that brings us to the foundational puzzle that really underpins this entire deep dive, the profound isolation of the brain. The sources highlight this by saying the brain lives in the dark.
I think we need to dwell on that for a second because it's so easy to forget. Your brain has never actually seen anything. It's never heard a sound. It's never touched reality.
It is the essential truth, and it's a bit unsettling when you really think about it. Your brain is a collection of about 86 billion cells encased in bone, floating in fluid.
It's in a dark, silent, temperature-controlled box.
Utterly isolated from the world you think you are seeing and hearing and touching. It receives no actual light, no sound waves, no physical pressure. None of the raw stuff of the world ever gets in.
So all that external energy, the electromagnetic spectrum that we call light, the pressure waves in the air we call sound, the chemical gradients we call smell, it's all immediately converted into the brain's one common currency.
Electrical spikes. Or nerve impulses. That's it.
That's all it has to work with. The richness of a Beethoven symphony or the incredible complexity of a sunset is reduced at the input stage to just patterns of what is essentially noisy electrical code.
So the brain's entire existence is one of constant inference. Its primary moment-to-moment task is to constantly guess what must be out there to be causing the specific stream of electrical noise.
It's a detective in a locked room with only a telegraph key clicking away.
That's a fantastic way to put it. It's a massive probabilistic effort to decode sparse and, frankly, often ambiguous data.
And what we call consciousness, this stable, rich 3D world, the sense that your body moving through space, that is the result of all that effort. It's the brain's current internal simulation.
Or, as we like to call it, the user interface. You are not experiencing the world directly. You are experiencing the brain's best real-time representation of the world. It's a model.
And that metaphor is so powerful because, just like any good user interface on your phone or computer, it smooths over all the complexity. It hides the messy code and the hardware running underneath.
And it sometimes produces lag or errors, right? We call them optical illusions. But it provides a functionally useful model for navigating the environment.
So if this conscious simulation is so widespread and coherent, where does the machinery actually live? I mean, we know the search for a single centralized consciousness center in the brain has been, well, a failure.
It's been completely abandoned. The modern view highlights critical networks, not centers. Consciousness is a team sport in the brain. It requires massive, long-range, synchronous communication. We can, however, identify maybe 3 key architectural components based on their functional necessity.
Okay, let's start with what you could call the rider, the central hub.
That would be the thalamus. It's a structure deep in the center of the brain, and it's the primary sensory relay hub. It routes almost all incoming sensory data, vision, hearing, touch, taste, everything except smell to the appropriate primary processing areas of the cortex.
But it's more than just a simple switchboard, right?
Oh, much more. Its role is far more than simple routing. It's a synchronizer. It has these massive feedback loops with the cortex. It helps to time and coordinate the dialogue between different brain regions. If the thalamus is severely damaged, or if its dialogue with the cortex breaks down, you get a profound, almost immediate loss of awareness.
Why so immediate?
Because the necessary information flow and that crucial temporal synchronization just collapses. The whole orchestra falls out of time.
Okay, so from the router, we go to the integrators, the big processors.
That's the cerebral cortex. Specifically, it's the massive ongoing conversation between the frontal and parietal regions in the back of the brain. This is where the synthesis happens. The spikes coming from your eyes are brought together with spikes from your memory.
Like, what is this object I'm looking at?
Exactly, and spikes from your bodily state, how do I feel about it? And spikes from your motor goals, what am I going to do next? This large-scale cortical interaction is what integrates all those streams, senses, memories, goals into that single, coherent, unified scene that defines what it feels like to be aware.
And finally, you need the power switch for the whole system.
You do. And that's the brainstem and the basal forebrain. These are evolutionarily ancient structures. They don't necessarily contain the content of consciousness, the color red or the sound of a voice, but they regulate the overall arousal and energy state. That is, wakefulness.
How do they do that?
They bathe the entire cortex in neuromodulators. These are chemical messengers like acetylcholine, dopamine, norepinephrine. These chemicals control the excitability and attention level of the entire network. They literally set the functional level of the whole system. Without them, the lights turn off, regardless of how healthy the cortex is.
So if consciousness requires this global synchronized activity, what precisely breaks down when the system loses coherence, say in deep anesthesia or a coma?
That's the key question. When consciousness is lost, brain activity doesn't necessarily cease. The brain isn't silent, but the functional topology, the way it's connected, shifts dramatically.
That's the shift.
The critical breakdown is in long-range communication. Local areas, like your primary visual cortex at the back of your head, might still react to a flash of light. You'll see a little blip of activity there.
But that signal doesn't go anywhere.
It fails to propagate. It fails to amplify and integrate with the distant frontal and parietal regions. That rich back-and-forth dialogue that's required for global coherence just collapses.
So it's like local chatter might be continuing in different offices, but the central company-wide announcement system has gone completely offline.
That's a perfect analogy. The global broadcast is gone.
This constant need for integration and the fact that the brain lives in the dark leads us directly to what is probably the most powerful modern concept in neuroscience: perception as controlled hallucination. This falls under the umbrella of predictive processing.
And this really flips the classical model completely on its head. The old view is that the brain is a passive receiver, just waiting for sensory input to arrive.
A blank slate.
Right. But the predictive processing model says the brain is a relentless prediction machine. It maintains a deeply detailed internal model of the world, and based on that model and the current context, it constantly generates predictions about what sensory signals should be arriving in the very next moment.
Okay, so give me an example. When I reach for my coffee cup right now,
before your fingers even touch the ceramic, your brain is already predicting the exact pressure sensations, the temperature, the weight, and the visual feedback that hand movement should generate.
So the data coming in from my fingertips isn't fresh news to the brain.
Exactly. It's not treated as new data. It's compared against the brain's prior prediction. The stable perception you experience, the feeling of a solid cup, results when the prediction and the incoming signal match. When they match, something called prediction error is minimized, and that's the key insight. The brain is trying to minimize error.
And what happens when there's a mismatch? if the cup is, I don't know, an illusion or it's full of ice when I expect it to be hot?
Mismatch generates surprise. And surprise generates a strong prediction error signal. This signal shouts up the hierarchy, hey, the model is wrong, and it triggers two things. First, a shift of your attention. You immediately focus on the cup. And second, an urgent need for the brain to update its internal model.
So you realize, oh, this isn't what I thought it was. The brain's model of reality is instantaneously corrected.
Right, the hallucination is brought back under control by reality.
This concept of continuous error minimization seems to explain so many weird mysteries of perception, like, for instance, the physiological blind spot in your vision. There's a hole in each retina where the optic nerve leaves, so the signals simply aren't there.
They're not, but you experience a continuous, seamless visual field. Why?
Because the brain predicts the field should be continuous, so it just uses the surrounding information to fill in the missing data. It papers over the hole.
Precisely. You never notice the hole in your vision because the brain's user interface is actively editing and smoothing over the deficiencies of the raw input. This is controlled hallucination in action. The brain's best guess is so compelling, it literally overrides missing data.
It also explains the speed of our conscious experience. I mean, if we had to wait for light to hit the retina, travel all the way through the thalamus, get processed by the cortex, our subjective experience would lag horribly behind the real world.
We'd be swatting at flies that were already gone. But the internal simulation is running slightly ahead of real time. By relying on predictions, the brain compensates for that neural transmission lag, allowing your conscious experience to feel instantaneous and stable.
So conscious experience, then, is simply the brain's current, winning, and constantly error-corrected internal model of the world and your body within it.
It's the most stable hypothesis the brain has running right now.
Now that we appreciate the scale of this thing and the architecture, this dark predictive network, we have to tackle the fundamental mystery. How does this system generate subjective experience? This is where the great competing frameworks, the big theories, come in, all attempting to define the minimal conditions for awareness.
And these theories are not just, interesting academic exercises. They represent fundamentally different strategies for locating and maybe even quantifying consciousness.
And they have enormous implications, right, for how we treat non-human minds, brain-injured patients, and of course, future artificial intelligence.
Absolutely. The stakes are incredibly high.
So let's start with the one that seems most closely tied to the network dynamics we've just been talking about. Global workspace theory, or GWT. This is fundamentally a functional theory.
Right. GWT uses this famous theatrical analogy, which was introduced by a psychologist named Bernard Bars. He said to imagine that the vast majority of processes in your brain motor commands, sensory analysis, emotional filtering, all happen unconsciously, in parallel. They're like actors and stagehands working backstage.
So most of the work is done in the dark, unconsciously.
The vast majority. And all these local unconscious processes are competing for access to the central global workspace, which is the stage under a bright spotlight.
And when information makes it onto that stage, into the spotlight, that is consciousness.
That's the core idea. But the definition of the spotlight is crucial here. It's not just that the information is amplified, it's that it's broadcast globally.
What does that mean, broadcast?
Consciousness, in the GWT view, is the act of widespread, high-amplitude broadcasting. The content, a perceived object, a memory you just recalled, a plan you're making, is shared simultaneously and efficiently across all these distant, disparate cortical systems.
So it goes to the language areas, memory storage, attention networks, your frontal executive functions.
All at once. This allows the system as a whole to coordinate its response based on that single important piece of information. Consciousness is the brain's internal bulletin board.
And the evidence for this seems pretty strong. I mean, imaging studies consistently show that when a stimulus is consciously perceived, it triggers this widespread, coherent activation all across the frontoparietal network.
It's a huge wave of activity. But if you show the same stimulus subliminally, too fast to be consciously perceived, the activity remains brief and highly localized. It just causes a little flicker in the visual cortex, for example.
It fails to achieve that global system-wide resonance. It never makes it to the stage.
It never does. So GWT defines consciousness as a mechanism of information distribution and utility. If the information isn't available to the whole system for action and for reporting, then by their definition, it's not conscious. It's a very compelling, very functional explanation.
But then we pivot dramatically to integrated information theory, or IIT, which is structurally focused and, to be honest, far more philosophical. IIT doesn't really ask what consciousness does, it asks what consciousness is.
That's the fundamental shift. IIT is what's called an axiomatic theory, which means it starts from what it claims are self-evident truths about experience itself. It starts from the inside out.
And what are those truths?
They identify two core properties that they argue all conscious experience possesses. First, it is highly informative, and second, it is highly integrated.
Okay, can you elaborate on what highly informative means in this context? It's not a word I usually associate with, say, seeing a color.
It means your current experience is incredibly specific. If you are seeing a green field right now, that single experience rules out the vast, almost infinite set of alternative possible experiences you could be having.
Like seeing a blue field, or hearing a loud noise, or feeling hungry, or remembering your childhood.
All of those are ruled out. The state is specific. An unconscious system, like a simple thermostat that just reacts to temperature, isn't informative in this way. It just has one state. The conscious experience is specific and therefore highly informative.
Okay, that makes sense. And what about the high integration property?
Integration means the experience is unified. It's a whole. You don't experience the color, the shape, the location, and the sound of a passing car as four isolated, separate components. You experience them as a single unified scene.
You can't separate them.
You can't. If you tried to break your experience down into independent parts, the whole thing would just collapse. That proves that the parts are all causally related and deeply integrated.
And this all leads to their famous, or maybe infamous metric, phi, which is an attempt to actually put a number on this integration.
Right. Phi is a mathematical measure of the system's causal structure. It's meant to quantify how much the system's whole is greater than the sum of its parts.
How do you even measure that?
In principle, you measure the amount of information generated by the system as a whole that cannot be generated by any of its individual parts or subsystems if you were to break them apart. A system with really high integration, with lots of complex feedback loops and high information generation, has a high phi. And according to the theory, that means high consciousness.
And this is where we see the really intense conflict with global workspace theory. GWT is all about the size and the functional distribution of a network, how far the signal travels.
Whereas IIT focuses only on the specific causal structure. It doesn't care how big the system is or what it's doing. It only cares about how it's wired internally.
So this leads to some pretty radical implications.
It does. For one, IIT makes the claim that consciousness is substrate independent. It doesn't need biological neurons. It just needs the right causal structure. Anything could be conscious.
And even more controversially, IIT posits that certain massive yet simple feed-forward neural networks, like some of the deep learning systems we use today, might have a phi value of near zero.
Exactly. Because while they process a ton of data, they lack the intense integrated feedback loops. They're like a long assembly line. You can break them down into independent components without losing very much information.
But GWT might look at a system that size, with that much information being broadcast, and argue that it should be conscious.
And that fundamental disagreement is probably the most exciting and hotly debated tension in the entire field right now. They make completely opposite predictions about certain kinds of systems.
Okay, let's move to the third major category of theories. Higher order theories. These seem to be more tied to our sense of self and reflection.
They are. These theories add a metacognitive layer, a sort of self-awareness requirement, to the conditions for consciousness. They argue that a raw sensory input, or a primary neural state, say, the specific firing pattern in your V1 visual cortex that represents a vertical line, is not conscious in and of itself.
It only becomes conscious when what happens?
When a higher order system, which they typically locate in the frontal lobes, forms a representation about that lower order state. In simple terms, you are only conscious of seeing the line when your brain also generates the representation, or the thought, I am seeing that line.
So consciousness is necessarily tied to the ability of the brain to monitor and represent its own internal states. It's consciousness of being conscious.
You could put it that way. This explains why damage to the frontal cortex, which is so critical for self-monitoring and executive control, is absolutely devastating to subjective awareness. It knocks out that metacognitive ability.
It provides the connection between consciousness and the sense of a subjective self. The state has to be available for this metacognition, the reflection about the thought, to achieve awareness.
And if you can't think about the fact that you're seeing red, the theory suggests, then the seeing itself is functionally unconscious.
Finally, let's consider the recurrent processing theories. These sound like a direct challenge to the necessity of that global broadcasting that GWT is so focused on.
They are. Recurrent processing theorists, sometimes called local theories, argue that GWT just overshoots the requirement. They maintain that consciousness does not require access to the entire global workspace.
So what does it require?
Instead, it emerges when information is held and processed in recurrent feedback loops within or between localized nearby cortical areas.
Okay, so a signal enters my visual cortex, it gets processed, and then instead of immediately propagating all the way to the frontal lobe, it just cycles back and forth between, say, layer 4 and layer 6 of the visual cortex itself.
Right. It creates a sustained internal reverberation. And that reverberation is the perceptual state. That's what creates the experience of seeing the line.
So basic visual awareness, for example, might emerge entirely locally in the visual cortex through this intense feedback.
That's the hypothesis. And the frontal lobes and the global networks, they're then needed only for reporting that awareness or for using that awareness in some kind of high-level planning. This gives you a very clean separation of labor.
The local loops create the awareness, and the global networks use the awareness.
Precisely.
Wow. So this whole collection of theories, you have functional broadcasting with GWT, structural integration with IIT, self-reflection with higher-order theories, and local loops with recurrent processing. It just shows how far scientists really are from agreeing on the fundamental mechanism, even if they can largely agree on the required neural real estate.
The map is getting better, but we're still arguing about what the territory is made of.
That structural debate leads us very naturally into our next section. What happens when we intentionally push the boundaries of consciousness? We're looking at altered states and how they reveal the fluid, almost illusory nature of the self.
And the anchor point for any discussion about the self, neurologically speaking, is the default mode network, or the DMN.
Right. This is a network that includes key areas like the medial prefrontal cortex up front and the posterior cingulate cortex in the back. And it's most active when we are not focused on an external task.
Exactly. When you're just sitting there, letting your mind wander. And its functional role is deeply, deeply self-referential. It's the network that's responsible for mind wandering, for internal simulation, for recalling past events from your life, projecting future scenarios for yourself.
And crucially, for maintaining the internal narrative, that coherent biographical story of who I am. It's the constant, subtle engine of the ego.
It's what generates that solid boundary between me and not me. Yeah. And so when we look at practices that are specifically designed to quiet that narrative-like, intense, focused attention in mindfulness meditation, we see a direct, measurable neurological change.
A decrease in DMN activity.
A measurable decrease in DMN activity, and also reduced functional connectivity within the network itself. Different parts of it stop talking to each other as much.
And subjectively, that decreased DMN activity corresponds perfectly with a reported feeling of ego softening or boundary dissolution. The meditator reports a sense of unity or a blurring of the self-world barrier.
The brain's generator of self has simply temporarily lowered its output.
Okay, so if meditation is like turning the volume down on the DMN, then psychedelics like psilocybin or LSD are like taking the DMN's volume knob and just breaking it right off.
That is a very accurate description. The sources highlight that these classic psychedelic substances act primarily via the serotonin 2A receptor, and one of their main effects is to specifically and dramatically reduce the integrity and internal coordination of the DMN.
The normal, constrained chatter of the self-narrative just stops.
It gets profoundly disorganized. But the disruption isn't just a shutdown. It's not like going to sleep. It's accompanied by a massive increase in global connectivity.
What does that mean?
Regions of the brain that typically do not communicate or only do so minimally, say your visual cortex and your auditory association areas, they suddenly start talking to each other rapidly and in very novel patterns. The whole system becomes highly complex and globally hyperconnected, but in a very disorganized, almost chaotic way.
And that neurological state, the reduced DMN constraint, combined with this increased global connectivity, correlates perfectly with the subjective experience of ego dissolution.
Perfectly. The internal narrator is silenced, and the rest of the brain is flooded with intense, unconstrained sensory input and bizarre cross-modal connections. This leads to those feelings of profound insight or unity with the universe. The usual filters are gone.
These altered states provide just this powerful evidence that our rigid day-to-day sense of I is really an elaborate, fluid, and computationally expensive model that's being maintained by this one specific network.
And when that model is disrupted, the subjective sense of identity can just evaporate, temporarily exposing the underlying, less constrained reality model that the brain is capable of producing.
Let's shift from the external manipulation of consciousness to the internal one, sleep and dreams. How does the brain maintain awareness when we remove almost all external input?
We have to look at the difference between the two main types of sleep. In non-REM deep sleep, what we call stage N3, awareness fades completely. The system is structurally online, the brain is using energy, but the activity is highly synchronized and very slow. All the neurons are doing the same thing at the same time.
It's like a whole stadium of people doing a very slow, synchronized wave.
Yes. And why does that synchrony lead to a loss of awareness?
I'm guessing because it's not very complex.
Exactly. High synchrony means low information content. If every neuron is doing the same thing, the state is predictable, it's simple, and it lacks the necessary complexity or differentiation to sustain a subjective experience. It's synchronized, but it's not integrated in a rich, meaningful way.
But then we hit REM sleep, or dreaming, and it's a complete 180.
It's a complete flip. In REM sleep, the cortical areas are nearly as metabolically active as they are when you're awake. The system is running these rich, often bizarre internal simulations we call dreams, with almost no external sensory input.
The brain is highly active, it's desynchronized, and it's integrated.
Right, which leads to a profound conclusion. Consciousness does not strictly require external sensory input. It requires a sufficiently rich, integrated internal model.
So the real difference between your awake reality and your dreaming reality is primarily the source of the constraints on that model. Is the model being updated by external physics, or is it just running wild based on your memories and emotions?
That's the core difference. And this leads us to some of the most poignant and ethically critical research in the field studying hidden consciousness in patients with severe brain injuries. This is where the objective measurement of consciousness becomes a matter of life and death.
We have this whole spectrum, right? From locked-in syndrome, where a patient is fully aware but has zero movement, all the way to a vegetative state where someone looks awake but shows no reliable signs of awareness, and then minimally conscious state in between.
And the problem is, for decades, we had to rely on behavior. Can the patient squeeze my hand? Can they blink their eyes? But behavior fails when the motor system is damaged.
The output is broken.
The output is broken. The groundbreaking discovery, which happened about 2 decades ago now, used fMRI to probe for awareness directly. Scientists found that some patients who had been diagnosed as being in a vegetative state, who could not follow any command, could still willfully control their brain activity when given specific instructions.
What were the instructions, and what did the findings prove?
They were very clever. The patients were asked to imagine performing 2 very distinct tasks. First, to imagine playing a vigorous game of tennis.
Okay, why tennis?
Because that task consistently activates a specific region called the supplementary motor area. Then, for the second task, they were asked to imagine walking through all the rooms of their house.
And that activates a different part of the brain.
A completely different part. The parahippocampal gyrus, which is involved in spatial navigation and memory.
And the unresponsive patients. They activated the corresponding region.
Yes. When asked to imagine tennis, their supplementary motor area lit up, just like healthy volunteers. When asked to imagine walking through their house, their parahippocampal gyrus lit up. This was undeniable proof of an intact capacity for communication, for comprehension, for intentional thought.
Which means undeniable hidden awareness, despite a total behavioral unresponsiveness.
It was a landmark discovery. And this research really propelled the scientific drive to create objective, reliable measures of consciousness to move beyond the ambiguity of behavior. The sources point to the development of what are called complexity indices.
Right, this is the current frontier. Scientists are working to quantify the richness of brain activity, regardless of whether the person can move a muscle. The most promising technique involves measuring something called the Perturbational Complexity Index, or PCI. Okay, how does PCI work? It sounds complicated.
The concept is actually quite simple. You deliver a strong, brief magnetic pulse, a perturbation to the cortex using TMS, transcranial magnetic stimulation, and then you use a high-density EEG cap to record the subsequent neural activity. You're pinging the brain and listening to the echo.
You're measuring how the system reacts.
You are. And if the brain is unconscious, say in deep sleep or under anesthesia, the response will be highly synchronized but very simple. The signal just dies out locally, or it spreads rapidly but uniformly, like a ripple in a still pond. This gives a low PCI score.
But if the brain is conscious, even if it's locked in and can't respond, what does the echo look like?
The pulse causes a complex, widely integrated cascade of activity. It reverberates across the entire network, showing rich, differentiated responses in different areas, but they're all still causally connected. It's like striking a complex bell with many different resonant frequencies.
So this high level of integration and high information content generates a high PCI score.
Exactly. And this index provides a potential objective physiological benchmark for determining the presence of awareness, regardless of the patient's ability to move or speak. It essentially gives us a quantifiable score for the complexity of their internal simulation.
We've established the biological and theoretical ground rules, and we've seen just how fragile the selves can be. Now let's cross fully into the philosophical and speculative realm, the frontiers where mind meets the deepest questions of physics and reality.
And we need to maintain a level of scientific rigor here. These theories are fascinating. They're brilliant attempts to solve the hard problem of consciousness, but they often lack the direct testability of the classical theories we just discussed.
So we start with the most ambitious and maybe most famous attempt to unify physics and mind, the Orcor proposal.
The theory of orchestrated objective reduction. It was proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff.
And what was their motivation? Why did they feel that classical neuroscience neurons and synapses was insufficient?
Well, Penrose, coming from a mathematics background, argued that certain features of human consciousness, especially abstract thought like mathematical insight understanding Gödel's incompleteness theorem, for example, involved processes that were non-computable.
Meaning they couldn't be simulated by a classical computer or by a system of classical neuron spikes.
Exactly. He believed that consciousness required tapping into a deeper, non-local, non-computable layer of physics. He was looking for a quantum explanation.
And their proposed mechanism is centered on these tiny structures called microtubules inside neurons. Why microtubules?
They are these tiny cylindrical lattice structures that provide the internal scaffolding for the neuron, but they're far more complex than just simple struts. Hameroff suggested they had the perfect structure to harbor delicate quantum mechanical states, specifically quantum coherence and superposition across large numbers of biomolecules within them.
So instead of consciousness being the result of classical electrical spikes between neurons, it's the result of the system engaging in quantum calculation within each neuron.
That's the core claim. They hypothesize that consciousness corresponds to the patterns that are created when these quantum states collapse, a process that Penrose calls objective reduction, which he controversially links to fundamental changes in the geometry of space-time itself.
And Hameroff added that this process is orchestrated by the classical inputs and outputs of the neuron, hence the name ORC-OR.
Right. They even claimed that anesthetic gases might work by disrupting these delicate quantum states within the microtubules, preventing the consciousness-generating collapse from ever happening.
It's a beautiful, elegant, holistic theory, but it faces one enormous hurdle that we just can't ignore: the decoherence problem. And we need to explain why that criticism is so scientifically devastating to the theory.
Decoherence is the process by which delicate quantum states lose their superposition and coherence the moment they interact with a warm, noisy environment. To maintain the necessary quantum entanglement and superposition for any useful computation, the system needs to be extremely isolated and cooled to near absolute zero temperature.
Like in a quantum computer lab.
Exactly. And the brain is the absolute antithesis of this. It is hot, it is wet, it is noisy, and it's constantly interacting chemically and electrically.
So the critics argue that any quantum state that might arise at a microtubule would instantly decohere on the order of femtoseconds.
Far too quickly to sustain the seconds-long coherence that would be necessary to generate even a single moment of subjective awareness. It's like trying to maintain a complex ripple pattern on a bathtub full of water while you're simultaneously throwing buckets of gravel into it. The noise just overwhelms the signal instantly.
So, while the idea that subtle quantum effects might play some role in biology remains open, we see this in photosynthesis and bird migration, the vast majority of mainstream neuroscience argues that the classical network dynamics we discussed earlier are sufficient.
And that quantum effects at this scale are not required to explain the phenomenon of consciousness.
Correct. ORCR is an incredibly intriguing philosophical project, but its proposed mechanisms violate established biological and quantum physics constraints simultaneously, which makes it incredibly difficult to test or prove.
Okay, let's move from quantum physics to a purely philosophical argument, one that seeks to solve the hard problem by sidestepping the idea of emergence entirely. Panpsychism, the mindful universe.
Panpsychism is what we call an ontological position. It's an argument about the fundamental nature of reality. It argues that consciousness, or at least a fundamental primitive component of subjective experience, often called proto-experience, is a fundamental feature of matter.
So it's like mass or electrical charge. It just exists everywhere, down to the level of elementary particles. That's the claim. And it's elegant because it completely avoids the question of how dead, mindless matter creates experience out of nothing, it says. Experience has always been there, from the Big Bang.
So it shifts the problem. Consciousness doesn't magically emerge when matter arranges itself into a complex brain.
Rather, the rich, unified awareness that we possess is the result of this universally present proto-consciousness becoming highly organized and integrated within a complex system like the human brain.
But if consciousness is everywhere, panpsychism immediately runs into its own most difficult hurdle, what philosophers call the combination problem.
And this is the critical critique. If every electron, every atom, every simple system has its own tiny flicker of proto-experience, how do a billion of these isolated tiny flickers combine to form one single, unified, complex, subjective whole, the singular you that is experiencing this moment?
The combination problem isn't just about combining information. It's about combining subjects. My consciousness is one unified thing. It's not a crowd of little consciousnesses.
And if panpsychism is true, we need some kind of mechanism that merges these millions of tiny subjects into one cohesive self. Currently, panpsychism has no coherent scientific or philosophical answer for the mechanism of this fusion.
So it's considered an ontologically parsimonious solution. It doesn't invent a new magic substance for the brain, but it simply trades the hard problem of emergence for the equally difficult problem of combination.
Exactly. It remains highly debated in philosophy. It's inspiring, but it's not yet grounded in scientific mechanism.
Finally, let's zoom out to the cosmic level. The idea of a global brain or a planetary consciousness. This feels much more metaphorical, but complex systems theory does give it a bit of a scientific anchor.
Right. This explores whether global, technologically mediated networks of human and artificial intelligence, the internet, communication systems, financial markets, data centers, could, in aggregate, constitute an integrated information processing system large enough to be considered a global brain.
And complex systems theory does confirm that large, highly connected networks can exhibit powerful, emergent behaviors that are totally unpredictable from just observing the individual components.
Think of a flock of birds or an ant colony. There's no leader, but the system as a whole behaves with incredible intelligence.
So the speculation asks if the massive information flow and density of human civilization could result in some kind of emergent cognition. Could the Earth, or human civilization, viewed as a metasystem, possess a kind of macro-consciousness? Or is this concept purely metaphorical?
Currently, it serves as a highly effective model for understanding global dynamics and complexity. But to claim it has subjective awareness, a giant planetary qualia requires us to accept a definition of consciousness, like the structural integration of IIT that we haven't yet proven applies to systems outside of biology.
It really pushes the boundaries of how far we can generalize the principles of mind.
It does. It's a fascinating thought experiment.
This brain binge has taken us on an incredible journey. From single electrical spikes all the way to quantum fields and cosmic minds. Let's try to bring it all back together with a final summary of the core tensions and the big open questions.
The central tension, I think, which really defines the current scientific struggle, remains the contrast between two paradigms. On one side, you have the view of the brain as a highly efficient, predictive, and mostly classical information processor. That's the GWT and recurrent processing camp.
And on the other side,
you have theories like IIT that insist the key is the subjective structure of experience itself. They demand a deep intrinsic quality, like phi, that exists regardless of what the system is doing functionally.
And the big remaining questions, those philosophical walls we just keep hitting, they're still completely unsolved.
Completely. First, there's the question of origin. Is consciousness a basic fundamental feature of the universe that's simply arranged and organized by complex brains, as panpsychism suggests? Or is it a purely emergent property that only appears when classical information processing reaches some currently undefined threshold of complexity or integration?
Second, there's a question of substrate independence, which is going to define the future of AI. Are we one unique type of conscious system constrained by our carbon and water biology?
Or could future AI built on silicon or alien minds built on vastly different substrates also be conscious if they achieve sufficient global coherence, like in GWT, or the right causal structure, as in IoT? The science suggests the latter is plausible, but we have no idea how to test it yet.
And finally, the most difficult hurdle, the one that the Penroses of the world are really concerned with. Even if physics and neuroscience achieve a perfect atomic-level description of the how every signal fires, how the information flows, how the networks integrate, will that ever truly explain the subjective why?
Why does the objective fact of complex information processing lead to the subjective feeling of being you? That explanatory gap persists, and that is the true hard mystery.
That brings us to our final thought for you. Based on our discussion of the default mode network and the possibility of panpsychism, consider this. If the sense of self, that internal narrator, is merely a fragile, constructed narrative running on the DMN, and if fundamental reality may indeed hold some primitive form of consciousness,
then perhaps the distinction between the internal constructed story of me and the external fundamental reality is far, far blurrier than we typically assume when our egos are intact.
the brain is trying its best to create a stable, predictive model. But sometimes, as these altered states show, reality might be much stranger than the simulation. Something for you to ponder next time your own self-narrative momentarily slips.
Absolutely.
Thank you for joining us on this Brain Binge. If you found yourself fascinated by the quantum field, predictive processing, or the search for hidden consciousness, be sure to subscribe to Brain Binge for more curious binges into the science of everything.
We look forward to diving in with you again soon.
That's it for this episode of Brain Binge. If you enjoyed getting your mind twisted tonight, do me a favor, comment, like, and subscribe so you don't miss the next deep dive. Got a weird fact, mystery, or place you want an episode about? Drop it in the comments. I read as many as I can, and I'm always hunting for new ideas. Thanks for listening, and thanks for letting your brain binge with me for a while. Stay well, stay curious, and I'll see you in the next one.